I want to return to looking at limits, especially limits that result in indeterminate forms like this. How do I evaluate each of these limits? Using the techniques we've already learned. Chris?
Let's go up and maybe look at the power limit.
Right. In this case, I would look at the highest powers. And since the highest powers are equal, not quite. When the highest powers are equal, I divide by the highest powers, right? So if I divide by the highest powers, I look at this, and then I say to myself, oh, 1 over x squared as x gets bigger and bigger and bigger and bigger, what happens to this piece? It gets really, so in the limit, it would become 0. Same thing with this piece down here. And that makes this a half. I really only need the leading coefficients. If I had naively said, well, just think about what happens as x gets big, I'd have infinity over infinity. And that doesn't really mean anything to me. That was our idea of an indeterminate form, and then we figured out how to determine it. What about this version? I can. What 1 would you like to multiply by? I'm not sure what x minus 2, again, would give me. I already have an x minus 2 on the bottom. But I could multiply by something else. If instead of multiplying by x minus 2 on the bottom and top, I multiplied by x plus 2, what would I get on the bottom? I'd get x squared minus 4 on the bottom. I already have the x squared minus 4 on the top. I also have this x plus 2. Those are going to cancel completely. Giving me something that I actually do have the ability to evaluate. I put 2 into that limit, and I get 4. Chris, I could also have simply factored the top instead to cancel the x minus 2s. But that multiplying by 1 is a good trick. I like to use it, and it still works. But both of these are resolved from an indeterminate form. If we think of just plugging in we would have written this as 0 over 0. I don't know what that means. And if we think about just plugging in, I'd get infinity over infinity. And again, I don't know what that means. Fortunately for us, we were able to do some algebraic tricks and resolve an indeterminate into a value. I like that. Problem is the algebra. In the same vein as these indeterminants, if I just plug in 1 on top and on bottom here, I once again get a 0 over a 0. If I plug in, quote unquote, infinity here, well, as x goes off to infinity, so does ln of x. As x is getting bigger, subtracting 1 doesn't do much for it. These are, again, indeterminate forms. The problem is there's no algebra that I can do here to factor or cancel or multiply by 1 or offer up a prayer to the heavens and go, please inspire me, I don't know what the hell to do. I would like to be able to still resolve this sort of indeterminate form. And really, to think of this, quote, properly, what I want to do is take apart the top and the bottom. So let's think about we're going to some number. And we have a situation that would look like 0 over 0. Each of those pieces, f of x and g of x, are equal to 0 as we approach a. What would a graph look like? If I graphed f and I graphed g, knowing nothing else about them, I would know they have an x-intercept there, right? So I don't know what the graph of f looks like, but let's make an assumption. Looks something like that. And g of x is going to go through the exact same spot on the x-axis. And what we're really trying to do when we evaluate this limit is we're trying to figure out the ratio of these two things, yes? If I asked you to take a real close-up of what's going on right at A, given the pictures I've drawn, those functions look really nice. So let's assume that we have derivatives there. When I take my close-up and you look at a function that has a derivative, what do you know about the close-up of the function at the derivative? Way back in chapter 2, section 7, 8, somewhere way back there. If I take a real small picture here and zoom into that little tiny box, what am I going to see? Near that dot. Yes, Chris. Well, because I have a derivative and I have a value. No, because I'm going to say the function is continuous there. So I shouldn't have a hole, I should have a dot. But as far as the graph of f or the graph of g is concerned, if I look at a really small area, the graph looks like a straight line. Not just any straight line, it looks like the tangent line. So if I zoom in tight enough, I will see f looking like a straight line. And I will see g looking like a straight line. And if I'm trying to take the ratio of these things, I might as well say, you know what, the hell with that. Let's take the ratio of the straight lines. But this line is going to look like that. It's got a slope at A. It's got an x-intercept at A, and it's got a y value of 0. And this line is g prime of A times x minus A. If I take, instead of f over g, if I take this line over that line, what happens? What happens right here? Those two pieces are going to cancel out, aren't they? Instead of f and g, I can use f prime and g prime. Holy crap, wait a second. If I have 0 over 0, and my functions have derivatives, then instead of looking at the original functions, I can look at the derivatives instead. This was in a letter, 1694, written by Johann Bernoulli to a gentleman, Frenchman, William Antoine Francois Marquis de l'Hôpital. Title like this, right? L'Hôpital wrote a book on the analysis of little quantities, which is what a derivative is about, right? He wrote this analysis book and published in it this idea from Bernoulli. It is now known as L'Hôpital's rule. if I have an indeterminate form, either 0 over 0 or infinity over infinity, because it turns out the same thing works then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a f prime of x over g prime of x. Bernoulli's idea said, since I've got these and they look kind of like straight lines close up, screw it, just use the straight lines. And since the ratio is the ratio of those lines, I can just use the slopes. Now, this allows me to answer the question I had earlier. That is an indeterminate form. If I just plug in 1, I get 0 on top, I get 0 on the bottom. Both of those are continuous at 1 and differentiable at 1. This is actually a consequence of Rolle's theorem, which is why we mentioned it before this crap. A number of textbooks will make a big deal out of the fact you need to look at the limit of the top and the limit of the bottom separately from one another. I'm perfectly okay if you were to say, hey, this is 0 over 0. But a lot of textbooks are very particular about that, and a lot of online resources are very particular about that. So if you go looking up examples, you'll see them look at each part separately. That's okay. But because I know I have this indeterminate form, by my buddy L'Hopital, I will always write LH over the equal sign whenever I do this. I can replace this limit by the limit of the derivatives. What is the derivative of ln of x? What is the derivative of x minus 1? Dividing by 1 doesn't change anything. So I get the limit of 1 over x. As x approaches 1, that's 1. Please notice I can even use this on the examples we already did. L'Hopital's rule still works there. I can also do this as we go out to infinity. Because as x goes to infinity, the graph of ln of x keeps going up. That's going to infinity. X minus 1, that's going to infinity. But if I use L'Hopital's rule, I replace those functions with their derivatives. What happens as x goes to infinity there? I get 0. No algebra trick required. A calculus trick supersedes it, but only when I actually have a derivative. Questions? If I think about ln of x going to infinity and x minus 1 going to infinity, I'm really asking which infinity is growing faster or slower than the other one. And this sort of comparison of rates of growth is used a lot in computer science to try and talk about how fast I can accomplish a certain task based on how much information I'm provided with to do that task, like sorting a task. Here's a giant list of things, sort them into numerical order. Here's a giant list of names, put them in alphabetical order. You do this in Excel by clicking two buttons. What's it doing? Big algorithm in the background. How fast that algorithm works, how efficient it is, how much time it's going to take to do the job is based on the idea of these sorts of limits. If you're going further in computer science, you'll see this in discrete math. The idea is something called Landau big O notation. If you're not going further in computer science, feel free to ignore that sentence. Unless you want to be rich. There's $1 million problem out there right now based on the idea of big O notation. Clay Math Institute Millennium Prizes. Look up the PNP problem. Thus endeth my diversion into computer science. In the same way, it is possible that when I do L'Hopital's rule, it doesn't fix anything. What happens as we go off to infinity, to the graph of e to the x? Draw me the graph of e to the x. You've got a graphing device. What's the graph of e to the x look like? And that means as we go off to infinity, we're going to the right, we keep going up and up. This is going to infinity. The graph of x squared, it's going to infinity as well, because that's my parabola. And as I go to the right, I'm going to infinity. So again, this is infinity over infinity. So I'm going to use L'Hopital's rule. What is the derivative of e to the x? Oh, good. What's the derivative of x squared? Houston, we have a problem. What's my problem? The top is still going to infinity, and now y equals 2x also goes to infinity. I did not change away from my indeterminate form. This is still indeterminate. If it's still indeterminate, and it's the right form, right? It's still infinity over infinity. I can do it again. L'Hopital's rule can be iterated. It can be done over and over and over until my indeterminate is resolved, if it is resolvable. That's a big if. But it should be, even if it takes me long. What's going to happen if I do L'Hopital's rule again? Yeah, if I do it again, the limit on the top is still going to stay e to the x. The derivative of the bottom is now 2. Yeah. I take it second derivatives now. I can also just think of it as Ion is taking the first derivative from up here. Right? It's like I ignore that this part ever happened and just say, hey, this gave me infinity over infinity. Let's do L'Hopital's rule. That's definitely not infinity over infinity anymore because the bottom's just 2 and there's nothing I can do to change that. But as x goes off to infinity, what happens to the top? It gets huge, and huge, half of huge is still huge, isn't it? So this limit is actually going off to infinity, and that means this limit goes off to infinity, and that means this limit goes off to infinity. The fact that I had to do L'Hopital's rule more than once to determine my indeterminate, that's fine. Sneaky, but fine. Now, this means that when we talk about relative growth, e to the x is getting bigger way faster than x squared is. Because if I think of the ratio of one infinity over the other, the top is much, much bigger than the bottom because of what we see as our result here. If the top was only twice as big as the bottom, my result would be 2. My top was only 4 times bigger. My result would be 4. In this case, it's a lot. It's infinitely larger than x squared. Just to, yes. Otherwise, it's a wild ass guess. In a very real sense, infinity is a weird enough concept. It doesn't make sense as a number. So we need to try and reconcile arithmetic with infinities. I don't know how to add infinities. I don't know how to subtract infinities. I don't know how to divide infinities. Well, now I can figure out what dividing infinities kind of looks like. Just like I'm not allowed to divide by 0, but 0 over 0 can be dealt with. And now it can be dealt with in a different way. I did actually go through a textbook and find a proof of L'Hopital's rule. I would like to point out to you, the actual proof is short, but it depends on knowing Rolle's theorem. So without Rolle's theorem, I would not be able to know why this is true. Questions? Try this one. First question. What does that little minus sign there mean?
From the left.
From the left. So I'm only looking at values that are smaller than pi. But sine of x is continuous at pi. I could just plug in. Cosine is continuous at pi. I could plug in. What did you do first? Those of you that have already written stuff down, what did you do first? Say again, Chris? Plug in pi. You should always try plugging in first. If my functions are continuous, I'll plug in. What did you get when you plugged in? Ooh, be careful here. If I just plug in, I agree with you that sine of pi is 0. But what's cosine of pi? Cosine of pi is -1. So when I plug in, I get 0 over 1 minus -1. I get 0 over 2, not 0 over 0. I can't do L'Hopital's rule unless I get 0 over 0 or infinity over infinity or some variation of that. So I must check first whether or not I have the right form to do L'Hopital's rule before I just go applying it. Questions? Because I have algebraic ability, I can extend the use of L'Hopital's rule. Let's consider this limit. The limit as x approaches 0, what's the little plus mean?
Right.
From the right, x times ln of x. The reason I need to approach from the right is because ln of x only exists for positive values. I can't have a negative get plugged into my ln. That makes my calculator go. So I start to look at this and I'm like, well, as we get closer and closer to 0, x is going to give me 0. But as we get closer and closer to 0, ln of x is going to do what? I need a graph for ln of x. At least I need to know the image in my head of what ln of x looks like. That's the whole thing. That's x times ln of x. Just look at ln of x for the moment. The graph of ln of x has a vertical asymptote at 0. And it's going down and down and down and down to negative infinity. Well, here's the problem. I'm multiplying two things together. I'm multiplying 0 times infinity. Infinity is so big, it's bigger than any number we can imagine. But when you multiply by 0, you get... This is like the unstoppable force and the immovable object. Which of these is going to win? Is the infinity going to cause everything to blow up? Or is the 0 going to cause everything to stop? I don't know. I don't know how to multiply infinity. Well, I do know how to divide infinity. Because that's what L'Hopital's rule tells me about, infinity over infinity. But this is 0 times infinity. And that 0 times infinity is still an indeterminate. But now it's an indeterminate product. And I only used L'Hopital's rule on quotients. So as far as I know right now, L'Hopital's rule is useless here. Unless I can find a way to change a product to a quotient. You've already done this. If I want to take something that's on the bottom out of the bottom, what do I do to powers? I have an x squared in the bottom. I don't want it in the bottom. How do I write it? Which is the same as 1 over x squared, isn't it? X to the negative 2. I can move stuff between multiplying and dividing by changing powers. So what if I take x times ln of x and write it as ln of x over 1 over x? I put it in the bottom, and just like you suggested, Jack, I made the power negative. Well, now the top goes to negative infinity. And the bottom goes to what's 1 over x as x gets really, really small. If x is tiny, 1 over x is really big, huge. That means as this gets closer and closer to 0, this is going to go off to infinity. The graph of 1 over x, we're coming from the right, graph of 1 over x goes up. This is infinity over infinity. I know what to do with that. I know what to do with that. I can do L'Hopital's rule here. The limit as x goes to 0 of x times ln of x is the same as the limit as x goes to 0 of ln of x over 1 over x. And that's something I can do L'Hopital's rule on. I don't care whether they're plus or minus. If the top and the bottom are both infinities, I can do L'Hopital's rule. What is the derivative of ln of x? What's the derivative of 1 over x? Unfortunately, no. If it's 1 over x, I either have to rewrite it to be a product, a power, or I have to use the quotient rule. If I write it as x to the minus 1, what's the derivative? Negative x to the negative 2. Hey, wait a minute. This top is x to the minus 1. What happens when I have powers like that? What do I do with the powers here? And that leaves me 1 on the bottom, doesn't it? A -1. The other way to think of it is I subtract the powers, the power on the top minus the power on the bottom. What happens here is x goes to 0. My immovable object beat my unstoppable force, the 0, 1. In this case, the 0, 1. I can only do L'Hopital's rule on division. So if I have something that isn't division, I need to do some algebra to make it division. In this case, this was the appropriate algebra to change a product to dividing by the reciprocal. Here's another one. The limit as x approaches pi over 2, again from the left, of secant of x minus tangent of x. Wait a minute. Tangent of x has asymptotes. And that asymptote is at pi over 2. That means this part is going to infinity. Secant of x same deal. Has an asymptote at pi over 2. This is infinity minus infinity? What the? I don't know how to subtract infinities. That doesn't make any sense at all. Again, if I can do some sort of algebra so that the result is division, then I can use L'Hopital's rule. Or I might be able to do some other algebra to make it easier. Secant, tangent. Those are made up of other trig functions, aren't they? What trig functions make up a tangent or a secant? Secant is 1 over cosine. Tangent is sine over cosine. Which means this is really 1 minus sine of x over cosine of x. Aha! Sine of pi over 2 is 1. So the top is 1 minus 1. Cosine of pi over 2 is 0. I know what to do now. I know what to do now. I'm going to put all of this over here in a bracket so that I know I was doing that off to the side. And now I can say, oh, this means I can use L'Hopital's rule. What is the derivative of cosine of x? What is the derivative of minus sine of x? Except I have this minus here. Because the derivative sine is just cosine, the minus sign stays with it. Those minuses cancel. If I put in pi over 2, cosine of pi over 2, we just did that. Sine of pi over 2, we just did that. Worked, Martin. Worked. We got it. If I can convert it from something that doesn't make sense algebraically to something that is a quotient algebraically, it's going to work. If you really want to stretch this idea, we can deal with powers. Think about 0 squared. What's 0 squared? Come on, people. What's 0 to the 17th? What's 3 to the 0? 5 to the 0. What's 0 to the 0? Well, it's either 0 because you're doing 0 to something, or it's 1 because you're doing something to the 0. I don't know what that is. That's indeterminate. If I had an infinity raised to the 0, something to the 0 should be 1, but this isn't a number anymore, it's an infinity. If I have 1 raised to any power, 1 raised to any power should be 1. So what if I do 1 to the infinitieth? Oh man, what the hell are these? If I want to deal with a power, I need to get it out of the power. How do we get stuff that's in a power down out front? The natural log. We did logarithmic derivatives, right? So the first thing I do is I put in an ln. And then I try and figure out if that's determinant. And maybe I'll need to do some other rearranging. There is an example in the text on page 315, example 9 here. That is gross as hell, isn't it? 1 plus sine of 4x raised to the cotangent of x as x goes to 0. Well, sine of 0 is 0, so this thing inside the parentheses is 1. But cotangent of 0 is undefined. That's where my asymptote is. That's an infinity. This is 1 to the infinitieth. If I do an ln first, then I get something I can do L'Hopital's rule on. But if I did an ln, I have to undo the ln. What do I do at the end? How do you get rid of an ln? With e. Once I work this all out and I get 4, that was the ln of my answer. So I have to make it e to the 4th to get rid of that ln. It turns out that these sorts of indeterminate powers have real practical applications. The way we came up with the number e was actually using an expression from banking. And remember I told you about the Bank of Sassmore? That's an indeterminate power. It's 1 to the infinity. And lo and behold, the answer turns out to be e. I will see you all on Wednesday. Have a wonderful rest of your day. Chase, homework.